We now have a car that can drive itself. It has a neural network for a brain that we can see right here making decisions, but they are not very good ones. So let's learn how to optimize this network. First, we'll continue to do trial and error, but we'll parallelize this so we have many cars going at once and we don't waste much time. Then I'll show you a more efficient way of doing this using a genetic algorithm that does mutation. I feel I don't need to explain what mutation is, but I will, and you'll see how easy it is to code as well. It's best if you code along with me, so open your project, and if you want to have this exact version I'm using, then get it from GitHub. And let's add optimization to your DNA. Get it? DNA? Because genetics... No! Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now. Testing here one by one these randomly generated networks and expecting some miracle is not very convenient. So let's write some code to parallelize this and have many cars running simultaneously, like in different parallel universes. I'm going to define here a function called generate cars that accepts n as the argument. And I'm going to have an empty array of cars at first, and then for I from 1 to n, I'm going to push a new car into this array. And the car is going to be centered in the middle lane at 100y with 30 width and 50 height, like so. And they are all going to be AI cars. And here I just return these cars, like so. And up here where we have car defined, we are actually going to define cars instead, equal to generate cars of n, like this, and our n is equal to 100. So we are going to have 100 cars going in parallel, and hopefully one of them is going to do something right. We need to update these cars here. So where we have here car.update, we are going to write a loop and say let I is equal to 0, I is less than cars.length I plus plus. And then we have here cars of I, update, like so. And we're going to do the same for the drawing down here, drawing them as blue, like this. But we still have two individual car objects here from previously. And I only need one car here, so let's just replace it with the first car in the array for now. Otherwise, this code will not work. So this is for translating the canvas on one car from the 100, and this is just printing the brain of this one car somewhere on the right. Save the file, refresh the page, and wow, it's a total mess. One thing we can do to make this nicer is actually draw them semi-transparent. So I'm going to go here and say car_ctx.global alpha is equal to 0.2. And after I'm done drawing these cars, I'm going to set global alpha back to 1 so it doesn't affect what I'm going to be drawing afterwards or on the next frame. So saving this and refreshing, it's a little bit better, but still quite much happening there. I think that I want to emphasize one car, like for example, the 0th car, this one that we are using everywhere pretty much, by drawing it again with the maximum opacity. but also I want this one to be the only car for which we draw the sensors. So I'm going to modify this draw method of the car next and say here a third parameter for draw sensor. This is by default set to false. And here, if this sensor exists and draw sensor, only then we are going to draw its sensor. And now it's a little bit clearer, not so many yellow lines there. And you can see something interesting already, that this car right here, car 0, is not the most interesting one. The most interesting one went somewhere up there and it was chasing the other red car. So back to main.js, here our cars of 0 choice is not really great. We want to focus on the best car, the one that goes upwards the most, or the one with the minimum y value. And I'm going to define this best car here and say best car is equal to find the car whose y value is equal to the minimum value, okay, of all the y values of the cars. So this may seem a little bit scary. So what is happening here, cars.map c going to c.y, this means that we are creating a new array with only the y values of the cars. That's it. And here we are spreading this array because the mathmin method here doesn't work with arrays. It works with many different values, no matter how many you want to pass it, but not with actual arrays. And that's why we need to spread it here. And we just find the car whose y value is the minimum value of all the y values. The code is not really complicated, but if you're not used to this modern syntax, then this can be a little bit daunting at first. I add it here because you will see it if you work with JavaScript. So now with this best car, I'm going to copy it everywhere we were using cars of 0 previously. So we translate the canvas to the best cars y, like this. And then here we are drawing the best car without transparency so that we clearly see it, and with the sensors. We are also drawing the brain of this best car. And that's it. I'm gonna save this and refresh. And now our canvas is always centered on the car that goes upwards the most. In this case, these stalking cars that are behind this red one. All right, let's try to refresh again. And again. I'm waiting for a car that passes this red car, but then continues to go in a straight line somehow. So just by trial and error, I think that we're going to be able to get to something like that. Let's see. Okay, we got something. It's fidgeting quite a lot, but definitely better than all other cars we had so far. It passed the car in the traffic and it's just going forward forever pretty much. But now the problem is that when I leave the browser, this car is gonna be gone and all my experimenting was for nothing. So let's write some code to save this car. I'm going to use local storage for this. So I'm going to say local storage set item, the best brain that we have so far, we're going to store it in this best brain attribute in local storage. And the value is going to be a JSON string coming from the best car's brain. So I'm essentially serializing that brain into local storage. And come to think of it, we might need to destroy this saved brain as well. So I'm going to discard, maybe it's a better word, the value from local storage with this other function. I'm sure it's going to be needed sooner or later. Now, this best car is actually not accessible here, so let me just update its value here, but define it here as a global variable, like this. I'm using let because it's changing, and I'm gonna set it to be the first car in the beginning, but it's gonna update on every frame. Now, if we have in local storage a brain, a best brain stored, I'm going to set the brain of this best car to the value. And I'm using JSON parse because I am parsing the JSON string we saved previously. Local storage only works with strings. Like this. Now in index.html, I'm going to put these buttons vertically between the two canvases. So here I'm going to use a div to define vertical buttons with ID vertical buttons. And I'm going to say here the first button is going to have an on click of save like this. And our second button is going to have an on click of discard like so. And here I'm actually going to use emojis for these button contents like this with the save icon and the trash icon. You can find emojis like this just by searching online. So I'm gonna save this file and go to the CSS next and remove this text align from the body because we're gonna use flex display instead. So I'm going to remove this and say display flex, justify content and align items to center like this. And now our vertical buttons are going to go here with display flex and flex direction column. So this is by default row, and making it column means that our buttons will go below each other. And here we define our button next. So I like to remove the border and give it a round shape, so a radius there, and a padding. This is some value that I found goes nicely with the emojis that we use, and a margin of 2 pixels, and the cursor set to pointer so that our arrow icon changes into a hand cursor when the mouse is over it. And speaking of hovering with the mouse, let's set a hover for the button so that it gets a blue background like this. So save the file, refresh the page, and looks like we have another shaky car over here. But we are not going to lose it this time because we can press the save button, and this means that now inside of our local storage we have this car's brain. So now when I'm going to refresh the page, what it means is that here inside of main.js, where we are loading the value from local storage, we still get the car from previously. If you're into anime, this is very much like when Naruto used shadow clones to speed up his training by doing it in parallel. Great idea, I think. Now, what we're doing here could be actually fully automated so that the computer tries again and again and always keeps the best. But let's think about what the goal is. I mean, what will a good network be able to do? Let's look at the definition of the best car here. We're just using the y-coordinate, but you can use other functions here as well. These are called fitness functions. For example, you could measure the travel distance instead. Doing that may result in cars that go backwards, as an easy way to avoid the obstacles. Or just go around in circles forever, going infinitely far but also going nowhere at the same time. So need to be careful when choosing a fitness function. I'm using the y value here, but if the road would be turning, it wouldn't work anymore. So think about these and play around with the code. And try to think about other stuff as well, like could you come up with a fitness function that keeps rewarding the car for going upwards but penalizes for going too much sideways? Or even better, penalizes if you're not in the center of the lane. These are all homework ideas for you, but now I think we're ready for more traffic. Let's go here in our traffic array, put a comma at the end, and add 2 more cars. One is going to be on lane 0 and minus, say, 300, and the other one at the same vertical level but lane 2. I'm going to save this, refresh, and now let's see what happens. Almost there. But it looks like even our shaky car didn't make it. So let's try again. It looks like there are just not enough cars passing that first car in traffic. What we would like to have is more cars like this shaky car, but not exactly like it, so that one of them maybe is gonna stand a chance and pass the second and third car in the traffic. So let's go now to network.js, and I will teach you how to mutate a network. And it may sound fancy, but it's really easy. I'll show you. We write here a method called mutate, which takes a network as a parameter and an amount. Let's default this to 1 or 100%. This will just randomize everything, what we had previously. But if you set this value to like 10%, then you're gonna get a network that is close to the original one that we pass it here. So how does this work? Well, we are going to go through all the levels of the network using a for each loop like this. And for each level, I'm going to use this arrow function notation here. I'm going to iterate through all the biases and then through all the weights later, but first with the biases. And I'm going to say that the ith bias is going to be equal to lerp. We're going to use linear interpolation again. And I will interpolate between the current value of the bias, whatever that is, and a random value between -1 and 1, as we did in the randomizing. But now we're using lerp to go from the current value of the bias towards whatever that random value is, depending on this amount right here. As simple as that. And I'm just going to repeat the same thing for all the weights. So I just go through all the ij weights like this and say that those weights, that weight of I and j, is going to be equal to linear interpolation between the current value of the weight and a value between -1 and 1, a random value. And again, depending on this amount. So if this amount is going to be, let me see, did I close this properly? Nope. So if this amount is going to be 100%, then we just get this part right here. And this mutate is pretty much our randomize method that we had previously here for a level. But now it works for the entire network. So if the amount is 0, then our biases and our weights just stay the same. But if this value is somewhere in between, then it's going to move away from these biases depending on this amount. So let me save this file now and go back to main.js, where we are reading the brain from the local storage here. And actually, we are going to loop through all the cars and say, let I is equal to 0 less than cars.length I++. So for each car here, cars of I, its brain is going to become equal to that from the local storage. So this as such is going to be really, really boring, right? Because it means that if we refresh now, we just see 100 cars that are overlapping each other and that are acting exactly the same. But I'm going to put here a condition and say that if I is not 0, so the brain that we have in local storage will be kept for the case when I is 0, and that is our best car initialization there. But for all the other ones, I'm going to mutate and say neural network dot mutate the car of I brain by an amount, let's say 0.1. And now let's see what happens. You can see many cars this time, but they are all following our shaky car quite closely. And this one, none of them was able to go beyond that second car in traffic. Let's try again. Nope. It looks like this 0.1 might be too low. Basically, our new networks are too similar to the one that we already have in memory. So let's try 0.2. Now our cars look a little bit more different than before, but still quite similar to our shaky car. And look at that, we have a new best car. Maybe. I hope it doesn't hit the border now. Yes, it figured out it has to turn. That's great. So I'm going to save this new car right now. And when I'm going to refresh, now our new car, the more improved car, which wasn't even shaking, is stored in memory. And it's going to mutate and try to become even better if possible. But our scenario now with 3 cars is not a match anymore. So we can try an even harder one. Let's go here and copy this maybe 4 more times. And here let's have 2 cars at -500 and the last at -700. And we are gonna have here maybe on lane 0 and lane 1, and then on lane 1 and lane 2. So I'm just thinking how to make a complicated scenario that involves all kind of twists and turns. So let's save this and refresh. And now let's see what happens. Oh, okay, I'm gonna save this. Phew! I did it before this other boring car overtook it. So that's something that you may want to pay attention to. Let's refresh. Ah, nothing. I think we want a lower value for the mutation here, so that more cars are gonna be like that one that almost went it past these other 2 cars. You can see quite many of them here now. Still nothing. Let's try again. Okay, this is interesting. I would say this is a new winner now. It got to this stage and now it's going in line with the other cars. Let's save it. It's taking too long. Let me try with 1000 cars. I think this should work on my computer. If your computer is too slow, then just stick with 100 cars and repeat more. Ah, almost there. Yes! Yes! We did it! We did it! Oh no, 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 no! Ah, I should have saved that one. I think it could have mutated into something good eventually. Huh? Let me save this, it's clearly better. Come on, I'm hopeful that this time we're gonna make it. Let's see. Okay, 2 cars there now. Will one of them stop before hit? Yes! Yes! That car stopped just before hitting the sides there. Let me save this. Try again. And now we have quite many of them that are quite similar. Okay, let's keep just one car here and see it in action without any other things disturbing it. Okay, that was quite close there. Oh, yes. Somehow I thought it's gonna get damaged, even though I know that it's the best car from previously, so it won't get damaged. There are many more sophisticated genetic algorithms out there. For example, some algorithms use crossover, so they take two networks and mush them together somehow. The hope is that maybe one car knows how to turn left really well and another one knows how to turn right. So combining these networks could give you a new one that can do both. Think you can implement this? If you got this far, I think you can. Try it out and let me know how it went. If you want to know some more advanced methods for optimizing these networks, you can check out NEAT. It's a scientific article that teaches how to optimize the whole structure, not just the weights and biases. Were you able to follow along? Then great. Please like this video if you learned something today, and share it with others so they can learn as well. And if you got stuck somewhere, comment below and I'll try to help. You can get today's code from GitHub, and the full code is actually already on my website. Check it out if you can't wait till the end of the course. See you guys.